So thank you everybody for showing up after lunch. And our next talk is ReInvestigating Powershell attacks with Matt and Ryan. I'm just giving over to you.
Thank you. Well, good afternoon, everybody. I'm Ryan Kazanciyan.
I'm at Hastings.
Thank you for joining us today. We're here to present for RetroCon ReInvestigating Powershell attacks. So Matt and I have a very similar background, a few years separated, but at largely the same companies doing largely the same types of work. So we both started in consulting at PricewaterhouseCoopers before then going to Mandiant, where we focused on incident response and forensics, and today at Tanium, where we focus on our product organization. We both live in Alexandria, Virginia, which, if you haven't been there, is right outside the Washington, D.C. area. And yeah, we spent a lot of the initial time when we were first creating the initial versions of this presentation doing incident response and forensics work. And today, we work on building software in part to help companies investigate, protect, and secure their environments. And so we effectively had made a transition between the original talks and today to deciding to go into product management. Although I assure you we're not going to talk about any product management stuff for today's presentation. So yeah, we first came to BruCON in 2014. Just out of curiosity, by a show of hands, who was here in 2014? Cool, a couple of you guys. How about 2015? A few more. Yeah, so 2014 was when we had first started this research. We found from YouTube the original clips of us doing this talk.
You know how you watch yourself on video or listen to yourself give a presentation and you think, man, I sound terrible. I looked at myself and I said, what was I thinking? I must have just come from Vegas because I have one too many buttons unbuttoned. And
it is an aggressive collar.
It is an aggressive showing. So today I'm thankful to say that I am fully buttoned up and I'm not showing as much as I was back then.
So we come back in 2015 to do the second part of our research on desired state configuration, and our spouses actually joined us, our respective wives, and so they actually got to sit in and see us present for the first time. And you can actually see in part of the clips my wife right in the corner here, although she eventually, I think, figured out she was in frame and then hid for the remainder of the talk. But I was hoping to get a shot of her asleep or falling asleep during our presentation, but lucky for her, she was out of frame for most of it. So yeah, we're going to begin by revisiting our Investigating Powershell Attacks talk. And just to set some context for those of you who hadn't seen that, when we started that research in 2014, it was in response to a incident that Matt and I had been working from the prior year, where the attacker had access to a victim environment through compromised VPN credentials that went back actually 3 or 4 years. And they had been detected and not fully remediated several times over in that environment. And what was interesting is after that last round of being detected but not stamped out, the attacker moved to a methodology where they were almost exclusively interacting with compromised machines after logging into the VPN through PowerShell remoting and in some cases just standard PowerShell scripts. And this was really interesting because we had never seen anything like that before. It was the first time any of us had seen an attacker utilize PowerShell in that manner in a targeted breach. It was by far the first time we had seen any sort of use of PowerShell remoting. And so we spent a lot of time basically learning the forensic artifacts of that type of activity as we went along. And what we ended up finding out is there wasn't actually a whole lot of good stuff to go with. So this is what prompted the initial research and what spearheaded the work that we did. At the time, there wasn't a ton of work done on forensic artifacts of PowerShell attacks, but there already had been some preliminary research on PowerShell and offensive techniques. And so we had started working with a lot of folks like Matt Graber at the time, who helped us along with that research. And what we did in that presentation was look at the forensic artifacts of 3 methodologies. One was local PowerShell execution of a script, 2 was PowerShell remoting, and 3 was configuring Windows Management Instrumentation, WMI, to persist a malicious PowerShell command line and run it on a system automatically. And we looked at the sources of evidence that each of those things produced on disk, in event logs, in memory, and over the network. So to recap some of the things we found back then, I'll talk about evidence in memory first. And this was in part driven by necessity because, as we'll talk about in a moment, in those days with PowerShell 2.0, PowerShell auditing was almost non-existent. And so we were really desperate to find any way to reconstruct any artifacts of activity, especially remoting activity, on a victim host. And so one of the places we looked was memory forensics. And what we had attempted to do was reconstruct the chain of processes that are involved when you execute PowerShell on a remote system via WRM, what that looked like, and most importantly, what actually could persist beyond the session. Because if you have an attacker interacting with the system over WinRM, and then the session ends, we wanted to figure out, reasonably speaking, if a forensic investigator took memory from the host hours, or minutes, hours, or days later, what would be left behind. And what we unfortunately found out was that the most verbose history about interaction over a WinRM session was pretty much non-persistent. It was in the context of the WSM prov host process, which gets spawned on a per session basis, and when the session terminates, that goes away, and your likelihood of recovering it goes away quite quickly. However, we did find that the actual payloads, the SOAP payloads that encapsulate the WinRM activity, did persist in the instance of service host that hosts the Windows Remote Management Protocol. And so between basically string analysis of that process space and string analysis of kernel memory and what was paged out, we did demonstrate that you could reasonably reconstruct at least artifacts of remoting activity, but with a quickly diminishing rate of likelihood of success. And so we proved this by, in this example, running invoke Mimikatz on a remote host via WinRM, then taking WinRM memory and finding that, yes, in fact, you could reconstruct some of the strings of that activity if you were lucky enough to grab memory from the host. But from a practical investigation standpoint, you would have to be very, very lucky to do that. And one of the interesting things that when we were revisiting this research that we noticed is there actually hasn't been a ton of work done on parsing PowerShell artifacts in memory since this, other than basic string analysis. I am sure you could go through the work of trying to reconstruct some of the native objects that encapsulate PowerShell in the different forms that you might run it on a system, but the fact of the matter is auditing and logging rendered a lot of that unnecessary. And so before we talk about what's new, we'll talk about what the state of PowerShell logging was back in 2014.
So as Ryan mentioned, in 2014, PowerShell 2.0 was probably by far the most prevalent version of PowerShell seen in the field. How many people in this room are going to be honest and say you still have systems running PowerShell 2.0 in your environments? Thank you for the 5% that were honest, and for the 95% that are lying, shame on you. And thankfully, as we've progressed, as version 3, version 4, version 5, and now version 6 has come out, logging has progressively gotten better, and we'll talk about that in subsequent slides. But even if you have done a good job and actually eliminated version 2 in your environment, or at least upgraded it, chances are you haven't restricted completely the ability to downgrade or to force the uses of PowerShell version 2. So in some cases, you may find yourself still needing to investigate legacy logging. And so there's two different approaches to this. There's the direct logs that are available, and then there's indirect evidence that you can find from other logging sources. From a direct perspective, there's not a whole lot there. So with PowerShell v2, you could really only answer the questions of when did something start, and when did something end? So my console session started and ended. I can now timeline around that activity. But from a core logging perspective, there wasn't much else present. If you're dealing with a remoting session, you could distinguish that from a local one, which is important. And if, for example, your security logs had rolled, you could still see the user account that was used to laterally access the victim system. But ultimately, you weren't getting a ton of information. The PowerShell analytic log is basically the output of event tracing, or ETW, which we'll talk about in a subsequent section later. But without some pretty strict controls wrapped around the analytic log, it becomes cumbersome very quickly. There's a ton of events that get created. But if you did turn it on and you looked at the logs, you could get things such as the name and the path and the user that executed certain PowerShell scripts. Then there's AppLocker. So everyone in here is running AppLocker in block mode across your entire estate and is doing that for both execution and scripts. 100% positive about that. But you also have the option of doing auditing. And so AppLocker has a nice way to audit the usage of both scripts and executables. So if you enable that, you'll still be able to see the actual scripts that are being executed, even if you're not going to be able to move forward with blocking them. And then transcription logging has largely surpassed in modern versions of PowerShell with some of the history that we'll talk about in a future slide. But on a per profile basis, you could log that, which would then, for each user that used PowerShell, log the specific commands that they were typing into the console. So here's just a quick example of some of the things that you could see. So in a standard user session, you would see the username is logging in. They're connecting via remoting. And then you can actually see a base64 encoded blob of the input and the output. Similar to how other things are broken apart, these are not always subsequent, and they're not in the same log message. You'd have to kind of reconstruct them after the fact. Doing so, you can see what this looks like when you decode it. So this is just, get child item from an invoke command of the root of the C directory, and you do see that it's present within the log if you're going to go through and decode it. So then PowerShell v3. So back when we were first giving this talk, this was probably the most impactful thing we recommended, was get on version 3 so you can get module logging. Because that was really the best approach to seeing on a per module basis what commandlets were being run for each PowerShell session. However, it turns out that also creates a lot of noise and a lot of logs. So as an example, when we ran invoke Mimikatz, in this instance, it generated almost 4,000 unique events in the log. So it's just a lot of data for you to have to go through and process. And then PowerShell version 4, script block logging. This was it. This was the holy grail, and it's still kind of, I would say, the standard for any script-based scripting language for how you can audit what's actually being used under the hood. I think most people, myself included, commonly refer to this, introduced in PowerShell version 5. It actually was introduced in version 4. And what this allows you to do is take blocks of code and log it into the event log. And what's nice about this is, in many cases, and as we'll talk about later, and as many people have shown, encoded commands or ways that you can obfuscate code to make it harder to read is actually then executed through the pipeline and logged as it's decoded. So not only do you see the actual compressed or the base64 encoded code, but as it's moving through the pipeline, it's decoded and also logged into the message. The nice thing here is it's also a larger format. So the max size of the event log message is what they use to truncate or break apart these messages so that it's much fewer events in the actual log.
And what's really impressive is if you think about the transition we just walked through, this all happened in a matter of like 2 to 3 years. And as much of a bad rap as PowerShell has gotten for the sheer amount that attackers have abused it in recent years, the fact remains if you were to actually stack up PowerShell against other scripting languages now, it's readily apparent that it offers far more from both a security control perspective and from a logging and auditing perspective. This image is from a recent Microsoft blog post that was basically making that point. And obviously Microsoft has a vested interest in trying to defend this, but the reality is, if you compare PowerShell to any of the other interpreted languages that are commonly supported across major operating systems, very few provide anywhere near the level of insight that PowerShell now can if you enable the options that are present with the most current version. And so from an attacker's perspective, that means that you have to evolve your techniques to be aware of that potential for auditing. And as a defender, you have better tools in your arsenal than you would if an attacker opted to use any other scripting language, including something like legacy VBS on a Windows host. And what's really cool about this is a lot of the great research and work that's been done to make PowerShell better and more resilient and more secure is now having a halo effect in making other interpreted languages better. And one of the things that folks in Microsoft have worked with the Python organization on is actually creating a standard for auditability and security transparency in future versions of Python. It's not in any of the mainline versions just yet, but I think 3.8 is actually targeting the ability to insert runtime hooks into Python 3.8 runtime so that you can actually start to capture and trace Python code in the same way that PowerShell script block logging works. So that is inevitable. I mean, the actual release timing of this is still a bit up in the air. But if you think of the many ways that we've seen attackers abuse Python code to do malicious things in real-world attacks, it will tremendously benefit from having this type of auditability built in.
So when we first gave this talk, we also gave an example and talked about, what frameworks we're using and leveraging PowerShell back then. And I think Metasploit had just introduced its first PowerShell payload, or the ability to interact with PowerShell on a compromised host. Cobalt Strike was about a year old and had just started kind of ramping up its capabilities. And PowerSploit didn't exist. It wasn't even Empire, yeah. Empire didn't exist. Powersplit. Empire didn't even exist yet. And we're going to demo Empire later, but I checked its GitHub commit history, and it was actually after 2014. But one of the things that we've seen is using PowerShell for attack frameworks has been largely commoditized and is used by a lot of red teams that are out there. And thanks to a lot of the advances in the PowerShell technologies for the blue teamers, it's become easier and easier to help detect this type of activities. But like anything else, the pendulum swings both ways. And so because of that, we've also seen a number of defense evasions start popping up. So probably most notably, and the one that's been talked about a lot, is Daniel Bohannon, who's sitting right here, his invoke obfuscation, which basically takes any kind of signature-based command line or any auditing and alerting and just breaks it apart. So it's really hard to then piece back together exactly what happened when you're doing things like breaking apart everything with tick marks and all the other cool evasion techniques that he built into this. Some of the other ones that I think are pretty notable are some of the script bypassing altogether. So there's things to bypass the AMSI actual prevention module built into PowerShell, as well as ways to turn off logging. So we'll talk about ETW as a logging provider later. You can actually turn that off. And then finally, I mentioned, PowerShell downgrade attacks. That's still a very real possibility where even if you have PowerShell version 5 and all the capabilities built into it, a well-funded attacker can easily downgrade that version of PowerShell to then force you back down into a 2.0 world. But at least from what we've seen some in the field is attackers don't necessarily have to invoke all of these to remain successful. So here's a couple examples. The first one is from a FireEye blog post citing APT32. And in this case, what they're actually using is a scheduled task that they're setting to invoke PowerShell. And if you look at the download string or the actual command line, it's something that can be pretty easily signatured off of. And if you're not flagging this today, you probably should be. The second one is another post citing a crypto miner attacker. Again, also a scheduled task that's just ultimately setting a suspicious looking command line. There's nothing really tricky there. A couple more examples. Probably the most interesting one that I thought was cool was the second one, where they're actually setting a WMI property and value and then reading data from that value and then piping it into the command line. But still, if you see that, you're going to signature off it. Like, there's no... I'll say this and I'll always be wrong. And I say there's no legitimate way that someone would be running this, and you're going to go back and find something. I can promise you that.
Yeah, the bottom line is that if you're looking for some of the most commonly abused PowerShell command line arguments and methods, you're going to still catch a tremendous amount of activity, including a lot of so-called targeted advanced bad. Not 100%, but the attackers are still in wide scale using things that work and are simple.
Yeah, I mean, there's no perfect solution. There's no silver bullet to security, and we'll have to continue to move the ball forward in advance and know that, whatever protections and methods of detection we put in place, there's always going to be some way to go around it, but that doesn't necessarily mean we shouldn't do anything at all. Here's a couple other statistics, from, I think in this case, this one's from Semantics, citing that only 4% of reviewed malicious code actually used any form of obfuscation. But at the same time, you see between Q1 and Q2 of this year, the amount of PowerShell being used has almost doubled. So this is another example of attackers just being able to more or less hide in plain sight without needing to go into the obfuscation world. So as a blue teamer, if you're looking at ways of identifying and detecting malicious PowerShell code, one of the first places to start is by baselining what legitimate PowerShell usage looks like in your environment. And I know this sounds like meat and potatoes kind of security practices, but it's actually pretty hard to do, especially when you're dealing in heterogeneous environments with different types of administrators who don't necessarily follow the same practices. But if you are looking to implement something like this, baselining that activity is a great first step.
And especially doing it over time. Like if you just take a point in time snapshot, you're not going to get a full picture. You're not going to see that like group policy script or that SCCM job that happens to run once a week or once a month. But over time, you can actually start to baseline and understand what is the enterprise tooling in my environment that is leveraging PowerShell, and use that to set that baseline and keep it accurate and up to date.
So where do I think we're going? As the field starts to catch up, the research community continues to move forward. And so as PowerShell, the interpreted language continues to add additional defensive capabilities and ways to keep people out, it seems like the community is just going below PowerShell. And so what we see now is an emphasis on .NET attacks. And so I've kind of submitted our abstract for BruCON 2020, where we're just going to be doing investigating .NET attacks. And I think 2 weeks ago, Ryan Cobb, who's one of the SpecterOps consultants, just released a completely C# tool-based for post-exploitation. And so rather than rely on PowerShell, he wrote the entire thing in C#. And I'm going to give a demo of what that looks like later. But one of the big advantages of going straight to C# is that you bypass a lot of what the scripting options are, or the logging options are in PowerShell.
So when we were updating this talk for BruCON, one of the things we wanted to do is talk about what's changed with the latest and greatest in PowerShell. And what's interesting is PowerShell v6 pretty much changes everything. That's not really an overstatement. So for one, it now has this awesome mascot, which cleverly has the PowerShell console logo in her face, which is kind of weird, but I guess makes PowerShell cool and fun. But yeah, PowerShell 6.0, the most fundamental change to it, and the reason why there's so many downstream impacts of that, is it is now based on the .NET Core 6.0 runtime. Which is meant to be fully open source and cross-platform compatible so that you can build on Windows, Mac, and Linux equally. To preserve the fact that .NET Core doesn't contain a lot of the components that .NET proper does, Microsoft opted to actually make this a fork rather than an outright replacement. So you can install PowerShell v6 side by side with PowerShell v5 on a system, and it in fact has its own separate shell, pwsh.exe, where you can live in that PowerShell v6 run space and run it side by side with a PowerShell v5 run space. So what does that mean for auditing? There's a new event log, PowerShell core/operational. There is a new event tracing GUID. Again, Matt will talk a little bit more about ETW later, but that's the GUID for that provider. And then finally, there are configuration files that specifically impact the audit settings for PowerShell. And we'll go into those in just a second, but those are the three I've listed there. The nice thing is that the events and the event IDs, at least for the time being, this is as of PowerShell 6.1, are exactly the same as PowerShell 5. So for example, the event ID for script block logging, I should say, is the same in this event log as it would be in the PowerShell 5 and prior event log. So that's not any different. I mentioned a JSON configuration file just a slide ago. So this is where you can actually configure the settings for things like what types and what levels of auditing are enabled. You can see here we've got a section for script block logging. Here we have something for execution policy. Here we have the transcription settings. And this is what's basically processed to determine how PowerShell is configured in PSv6. One of the interesting ways that you interact with this to actually enable and register a configuration if you've changed or added something like that is a script that is shown here, register manifest.ps1. So if you're an administrator on an endpoint and you run that script, you're effectively registering whatever configuration is serialized in that JSON file. And then what's also interesting about that is if I run this simple unregister switch, I now disable whatever settings have been enabled. And so it is actually that simple to turn off auditing in PowerShell 6.1 as long as you have sufficient privileges to do so. Now, that leads to the natural question, well, how do you determine if someone turned it off? There is no event that actually is thrown in the event logs when you run that unregister command. However, it is captured in transcription logging. So one of the nice things is transcription logging is actually enabled by default. So if you have transcription logging, you'll actually see the command line of running that unregister command captured, and you can look for that to identify if someone's tampering with logging or not. But at least as of the initial research we did, we didn't find a discrete event that was thrown when a config change like that happened. Another thing that's interesting is, in addition to the JSON configuration, so that organizations could configure PowerShell 6 logging via group policy, they also added a means by which you can do so with a registry change. And so that's what's outlined in this slide here. And you can see some of the underlying code that I've snippeted here, just showing you what the key value names and data are to toggle the various settings. Again, what's interesting is if you use the register manifest script, it doesn't actually set the registry keys to reflect whatever's in the configuration JSON. So they're kind of kept independently. Didn't have time to deeply research how the system deconflicts if you have conflicting configurations between the JSON and what's in the registry. But know that if I just run the script on its own, I'm not creating or setting what's in the registry. You have to do that separately. It's managed completely out of band. And again, I think the purpose for that was an enabler for group policy to interact with these settings. And then finally, there is a persistent command history, which you can think of akin to bash history. Matt had actually caught this when doing his testing with me on this. And so there's a history text or console host history text file that you'll find within the specified path there. You can also look at, what is that get PS read line option again? Is that the settings or?
That's the settings.
That's the settings, right. But that text file will give you, just like bash history, a complete rundown of everything that executed. And so even if you have transcription logging disabled, the command history to a default, I think, of 4096 commands will tell you everything that ran. So that could be another way that you could determine, for instance, whether someone disabled logging. All right, so that's what's updated with PowerShell v6. On to our second talk from 2015 on desired state configuration.
So we were fortunate enough to come back to BruCON the following year in 2015 and gave a talk on a subject that we were sure at the time was going to be huge. And it was based on something Ryan had found, which was desired state configuration, which is basically an out-of-band means of managing systems to a desired state. It's really designed for servers that you need to manage that are, let's say, built in the Azure cloud or just somewhere off premises where you wouldn't be able to set them via GPO or whatever it is that you're using to configure. So we did this talk on desired state configuration, and we called it DS compromise. So a quick show of hands, how many people know what desired state configuration is?
Wow, that is a lot more than when we did this in 2015.
Yeah, it's going to take off any day now, I promise. But what's cool about it is that it does allow you to use an out-of-band method to enforce configuration on a machine. And that configuration can be, ensure services are set, ensure processes are running, ensure user accounts are present in a specified directory, or just run scripts. And so from an attack perspective, we thought thinking about, well, what can we actually do with this? How can we set this up? And the first thing we did was understand the architecture. So there's two different means of which you can manage these systems, either by a pull or a push message. So if you're pushing, this is going to use WinRM, so the same remoting service that PowerShell uses. But if you're going to use a pull, this can be done either via SMB, HTTP, or HTTPS. Now that's interesting, because then you can, in theory, set a system on the internet, have it as a malicious configuration server, and then compromise a machine inside of a network and configure it to go out over HTTPS to pull down its malicious config. And that's what we set up. So a couple of things that also made this interesting. During 2015, when we did this talk, that we really cited this as a means of an alternative persistence technique that allows for recompromise automatically if a system is not properly remediated. So if you don't know to look for this, and you just, let's say, delete a file, remove a registry key, kill a process, the system will automatically reinfect itself with no need for the attacker to actually interact with that machine. And so if you're not looking for it, you can very quickly miss something like this. The other thing that we thought was interesting is that this was not captured by Windows auto runs. And so we took the initiative to email Microsoft, and we actually got a reply from Mark Rasinovich saying that this is the kind of thing that we should be investigating, or this is the way that we should disclose these to Microsoft. And in 2018, it's still not there. So unfortunately, it's still not a part of auto runs, but we've also haven't seen this really pick up steam or become too popular, but we'll touch on that here in a minute. So what we really built in 2015 was what we call DS Compromise, which is just a framework of streamlining this process, because one of the consequences of DSC that I discovered quickly is that it's really hard to do. And maybe that's part of the reason why it remains so unpopular, but it was pretty hard to get the whole thing set up. So we built a PowerShell module that kind of makes the whole thing pretty simple and focuses on two different ways. One is setting up your malicious server, so configuring it with what you want your victim machines to pull down, and then just setting a script on your victim to configure it to point at the server to pull down the right configuration file and then apply it. And that's really what it was done. And it was done via HTTPS with the thought that, if you were going to use this, you could set it up as either, an internet-facing machine, or if you wanted to be pretty stealthy, you could set it, internal to internal. However, when you do set up a DSC server, it does require downloading a number of different modules and commandlets that are not there by default. So we implemented a couple different payloads that we thought were interesting to show. The first one was persisting malware. So we ensured a process was running and a file was present, but we didn't set it as persistent via service or anything else. But the script itself ensured it was persistent. So if a user came in and deleted or killed or did whatever they needed to, it would automatically reinfect itself on an interval. The second was persisting a user account and ensuring it was part of the local administrators group. And in our demo, which unfortunately we're not going to have time to show today, we went through and deleted the account or just removed it, and the system went back and immediately set it in. It's also not really logged that well, and Ryan will talk about some of the sources of evidence, but it's not always intuitive exactly what's happening.
Yeah, and so the reason we pursued that research was after struggling with the PowerShell attacks that we talked about earlier, we thought that we'd try to lean in and figure out what new thing attackers might figure out, and the intent was, if we can come out and expose a potentially abusable technique, then we can also come out and provide sources of evidence before it's actually seen in the wild. And so people will be prepared to detect and defend if this actually ended up being adopted by attackers. And so half of our presentation was focused on the scripts and the tooling that Matt described to make it really simple to at least abuse and weaponize desired state configuration. And then the second half focused on the ways that you could identify and detect and investigate whether that happened. And so we had identified a few different sources of evidence that we'll quickly recap here. The first was network activity. So if you had the payload configured to use pull mode and retrieve a malicious configuration from an internet hosting system, it's pretty apparent if you have something like web proxy logging, because normally you wouldn't expect endpoints to be pulling down the URLs that are shown here. And these are basically the distinctive locations that when you've got a system configured in pull mode, it uses to yank down the configuration that it's set to retrieve. So that's very easy to detect on the network. On the file system, this is going to be a bit small here. I'm not going to run through it line by line, but if you have any sort of EDR tooling that is doing the continuous black box capture of process and file interactions, something like Sysmon, something like any of the out-of-the-box EDR products, they're going to record the file system activity that results from a DSC configuration being set into place, and it's pretty noisy. You can see that when you configure a system for the first time, there's a lot of setup that goes into the LCM, the local configuration manager. There's a scheduled task that gets created. There's temporary and then permanent versions of the MOF files that retain the configuration itself. And then if you're using our infect host with malware scenario, there's also the payload that's dropped as part of that malicious configuration. So if you're monitoring at this level or doing post-intrusion investigations, it's really apparent that something nefarious is going on if you're looking at this level of telemetry. And then finally, as Matt mentioned a moment ago, event logging for desired state configuration, at least at the time, wasn't great, but there were enough events, at least in the default DSC operational log, that you could know someone is implementing a configuration on a system. Here's the GUID for that configuration. If you wanted to detect whether a rogue config was being pushed to systems, there is absolutely an event that you could capture and hunt for or forward to a centralized event collector. Is this me?
Yeah.
Oh. All right, state of DSC attacks. So here we are in 2018. As Matt has been hinting at, we had high hopes that this might be a compelling and interesting avenue for researchers and attackers. And what we ended up finding is that the state of DSC attacks in 2018 is pretty much captured here. nothing has really happened in this space since we embarked on this research. And I think there are a bunch of reasons for that. The first is this stuff is really complicated to use, and it's really difficult to troubleshoot when things break. And we had attempted to simplify some of that from a red teamer's perspective with the code, which Matt mostly authored. But
that's a well-maintained Git repo if I've ever seen one.
I don't know what that little surge of activity was in 2016, but like, looks like you found some bug that you stamped out or something.
Oh my God! I don't even
But
know
yeah,
what I was
it's been pretty quiet. It's still not in auto runs. Maybe that's okay, given that this isn't really widely used. But yeah, if you're looking for evidence of this in auto runs, it's still not there. And these were the bullets that we actually had in our original presentation, and I think they're still true. Like, why is no one using this technique? One is that it's difficult to learn and use. Two is that it has a version dependency, and in most modern Windows enterprises that we find, Windows 7 is still really prevalent, which means unless they've explicitly upgraded PowerShell, they don't have the minimum version necessary to utilize a lot of this, which is PowerShell 4.0 on the victim host. And then on top of all of that, again, this is a post-compromise persistence mechanism, not an initial means of entry, and so the attacker has to have administrator access to the host already, and the reality is there are many, many more covert ways to persist on an endpoint that also happen to be easier for an attacker to wield than mangling this configuration engine. Now, all of that being said, we had a tremendously validating moment just a couple of months ago. When was this? Actually, back in March. So Matt Graber, who we mentioned earlier, we worked with Matt back when we were at Mandiant, continue to really benefit and admire from the great research that he did with a lot of others in the PowerShell community. But he finally got around to looking at DSC earlier this year, and so he tweeted a tool that he put on his GitHub that basically used DSC for simple lateral movement, basically a remote process create, and posted the POC for that, and then in a subsequent tweet mentioned that he finally checked out the talk that we did, the version of this we did back at Black Hat in 2016, and gave us some love. And so this was totally a Senpai Notice Me moment where we're like, yay, someone finally looked at the research, and it was Matt. But yeah, that really has been, from everything we found, the only evidence of anyone using this in the wild, either to carry forward an attack technique or for a researcher to find additional ways to abuse it.
So someone once contacted me on Slack and asked me a question about it, and they said they thought their red team had used it. And I helped them out through the evidence, and it turned out they were just using WMI.
But yeah, so let's talk about changes. So just as we mentioned, PowerShell v6 changed a lot. The same thing is happening for DSC. And I think, again, this is part of why attackers are not going to rush to this, because anytime you've got a moving target like this, enterprises aren't going to rush to adopt it, and that means that there isn't a sufficient ecosystem for attackers to bother leveraging it because the economics are just not there. So what is Microsoft doing with DSC? They're now transitioning to what's called DSC Core. So DSC still has some relevance. If you're managing an Azure environment, you're probably using DSC for some of the administration and orchestration of that. But what DSC Core intends to do is make DSC cross-platform open source in the spirit of the .NET Core foundation for PowerShell v6. And so to do that, what's really interesting is it is completely stripped of dependencies on WMI and the Windows Management Foundation. There is a completely new local configuration manager that is written to be cross-platform so that DSC Core can support Windows, Mac, and Linux. And by virtue of all those changes, that also means that resources for configuration are now in DSC Core can be implemented in native C or C++, in Python or PowerShell, and that's PowerShell Core, because again, this is all predicated on .NET Core. The design work for this is still underway, and Microsoft initially announced this direction in early 2018 or late 2017. Just a week or two, they basically posted an update saying that there is still no concrete date where this is going to be delivered. I am somewhat skeptical that this is going to see a lot of traction outside of potentially where DSC already has a footprint in managing Azure. I'm not sure how much cross-platform use it really will get, but it's something that will remain interesting, especially given the fact that resources can be written in this much wider array of languages. So we'll see where that goes. But yeah, off to ETW.
So in our last section for the day, we're going to talk about ETW, which is not something we've presented at BruCON before. So ETW, or Event Tracing for Windows, has been around for a really long time. And it actually started back in Windows 2000, but became prevalent in Windows Vista. And I think a lot of people have heard of ETW, kind of know what it is, know that it was originally designed for things like performance monitoring and application troubleshooting, but it also serves as a really good forensics tool that's really hiding in plain sight. So as an example, I pulled some metrics, and things like Process Monitor use ETW. They just don't advertise it. NetSH uses ETW. DiskMon uses ETW, as well as Performance Monitor. All of those use ETW providers under the hood. And there are actually hundreds of what they call providers available to you to use from different applications, from the actual Windows kernel itself. And how it's all instrumented is in these things called sessions. And so sessions are just a picking and choosing of different available providers. So again, there's hundreds of providers out there. So there's an IIS provider, there's a file system provider, there's an IE provider, there's really a provider for almost everything that's on the system. And depending on what roles are installed, can dictate what providers are there. And when they're in these sessions, you can have multiple providers into a single session that are then configured to log certain types of events or keywords. Otherwise, it will flood you with events. So one of the downsides of this is this was meant for debugging. So it can very quickly generate a huge number of events if you're not careful. So you can actually monitor every single thread and every single thread call that this thing makes. And you can imagine what that does is it will quickly overwhelm these buffer pools. And so then you have a means to process these events. And so you can do two different things. You can log them out to an ETL file. So this is, if you look at the analytic log in your event viewer, that's an ETL file. Or you can process them async as they get created in memory. So what we're going to demo today is being written out to a log file, but in practice, if you wanted to do this across your state, you probably want to do more of a real-time delivery implementation. So here's a couple of examples of providers that we found to be forensically significant. So probably the biggest one is the kernel process, which is actually a kernel level provider that provides, information directly from the kernel into user mode or user land applications. So these are things that track, thread creation and execution, DLL loads, and process execution. There's also a PowerShell provider, and so this is where things like all the PS modules that are run, as well as script block logging, can also be written to. The DNS client logs all DNS requests, kernel network connections, and logs your file system. So what's nice about these is these events are not done in a vacuum. So they're not created just by themselves. They're actually linked back to the specific process and thread that created that event. And so using that, we can then orchestrate and build back a complex object of everything a process did. And that's what we're going to demo here in a second. But it's basically a way of organizing and starting an ETW session using the providers I just mentioned to then capture details and link them back to the processes that actually generated the activity. So one big thing about this is also impacted by any kind of PowerShell evasions. So if we talked about earlier how you can bypass a lot of PowerShell logging, this is unfortunately impacted by that as well. So what I'll demo here is an out-of-box forensic collection while we're compromising a machine, and then we'll walk back what we're actually able to recreate. So this is also very useful beyond PowerShell. There are certain processes that are not going to be PowerShell only that I'm going to demo, so this is not a PowerShell only collection. So here, let me see if I can do this without completely botching this up.
I don't think we've ever done a live demo at BruCON. We did videos for the DSC talk.
This is a video. All right, so what we're going to do here is we're running Empire. There's going to be a victim machine that's going to be compromised. That victim machine is running this ETW forensic collection throughout this whole process. So the first thing we're going to do is get onto the victim. In this case, we're going to be a standard user on a domain-joined machine who has no real privileges. So here I am as norm no admin. And then what I'm going to run is a command that's using CERTutil to download and execute a PowerShell script from the internet called get GP password. And basically what this does is it identifies domain-joined machines that have hard-coded configuration passwords in them and then gives them to you in plain text. So now I'm going to elevate myself to run as an administrator. So now that I'm an administrator, we're going to go ahead and open up Notepad and create a VBS script. And in this case, it's going to be the Empire agent. So so this is going to launch PowerShell that then downloads and runs the Empire agent. So here's our stager, and now if we move back, we can see that we have an initial client. So I'm going to go ahead and interact with this and get some information. So now I'm interacting with this machine remotely, and I'm going to go ahead and inject into the spool SV process. So now that I've injected, I'm going to run a couple other commands. All right, so kill the original agent, then I'm going to interact with the injected agent. All right, so you see now we're in the spool SV process, and we've now injected into this, and we're going to run, shell q user, and then run mimikatz to dump credentials. And then just run a netstack command. And at this point, the attacks part of this demo is over. So as I mentioned, during this whole period, we've been running just an ETW collection. And so then for the second half of the demo, I'm going to kind of walk through what that analysis looks like. So here I'm running PowerShell version 6 on my Mac, and so I am really hoping everything works out well. So you see there's some interesting spaces. All right, so I've imported the module, and I want to see what the different commands that we have. So one of the things that I built into this module is a way of interacting with other ETW providers. So the intent was not to just give an out-of-box way of collecting forensic information, but also inspecting, identifying, and using other interesting ETW providers. So I'm going to give an example of a new one at the end, but just to give you an idea, like I said, there's hundreds of them on any given Windows machine, and we're using, I think, 6 today. So there's a lot of other options out there if anybody wants to take the time to actually go in and look. So in this case, I'm going to just import the demo XML. So as an example, because I didn't do a ton of filtering on this session, that 2-minute demo generated probably about 100 to 200 megs of logs. So that gives you some idea of the scope and the scale of what you can get with ETW. And then, the hard part in this case is actually parsing it down to make it so you're not constantly being flooded with logging events. So the first thing I'm going to do is just look through my session and pull out any instances where PowerShell was run. So here we have the process ID as well as the process path. So I'm going to take a look at the first one and just see all the different properties that are available to me to look at this session. So we can see things like child processes, the command line that was provided to it, what commands they run, the create time of the process, IO, DLLs that were being loaded, and a number of different things that we'll go into during the demo. So let's take a look at all the different commands we ran in this single instance. So this was the get GPP password. And so in this case, this is similar to not only module logging, but you're also getting things like who am I and other types of, oh no, and other types of sub-processes that are being run in this specific PowerShell instance. So now we can say, okay, well, show me all script blocks. So in this case, this will look at and reconstitute all script blocks that are logged and then provide them into different objects. So this is all the source code for get GPP password that was downloaded via the internet. So in this case, let's look at all the different child processes that we ran in that first instance. So when we were interacting with this machine, we ran whoami/all to verify you are norm no admin, and then we ran CERTutil to then download the GPP password text from GitHub, and then we did run as administrator. So all of these things are captured and logged as child processes. So now we're going to take a look at CERTutil. So you see here, we can already kind of see some of the information that you get, all the threading information, all the different loaded images, the file system activity, but we can also drill into that. So here we can check all the domain lookups and the IPv4 addresses, and then just verify that it matches our network connections. So in this case, we can confirm these are the domains that were looked up, and these were the addresses that the script actually connected to. Here's run as. So this is when we elevated ourselves to become an administrator on this box. So we see that then we ran command. So I'm just going to go look at this. And then we see, we started notepad launcher.vbs, and then we actually executed it with C script. So, and then we can confirm that this is where we launched and written to launcher.vbs. And sure enough, we can verify that with C script. Yep. And then so here's the second instance of PowerShell that got executed. And so this is the PowerShell command that was executed via launcher.vbs. So in this case, they're really not taking much, they're not being too careful in obfuscating their command lines. In this case, we just have a base 64 encoded command. And then similarly, we can do the same thing that we did before. So look at all the different commands that were actually run. And in this case, we ran invoke Empire. So this is the actual source code from the Empire agent. So again, this was downloaded and invoked and not really written to disk too much. And then we were able to capture it and log it with ETW. So there are a couple things that were written to disk. So here's some of the examples. And you also see that in this case, you can have create and deletes. You can also enable reads with ETW, but I highly don't recommend that. There's a lot of file system reading that goes on. Similarly, we can look up, these domain lookups. So this is the C2 address for our Empire agent. And here are the connections associated with that. One of the other cool things that you get after a process exits is you can see, similar, almost NetFlow data. So you can see the full, the transfer kilobytes read and written as part of a process's instance. So if a process is writing large amounts of data, you can sometimes recreate this back to determine, was there some type of data theft that took place. So here's another one where we can actually see all the different DLLs that were loaded. So another common technique, is to use the automation DLL, which is really the DLL that PowerShell uses under the hood, and then use that in lieu of using PowerShell. And so in this case, when we injected into spools SV, we injected into this 1924 process. So this is the second process that looked up the domain, let's pop a box. So you see here that the image name is blank. The reason it's blank is that this process started before we started our collection. So we didn't have the process create event that we would normally see if we had this running before the process started. So in this case, we don't get the image name or the command line. That's one of the limitations. You can only see things that you're monitoring for going forward with ETW. But if we look at the file IO on process ID 1924, it's pretty obvious what this process really is, because it's really writing only to the spool drivers directory, which is what spools SV is going to do. So then we can look at all the child processes of spools SV, and if you've injected into this is definitely something that would stand out. And if you look, these are all the different child processes that were actually executed from our attacker's session. See that the domain lookups took place. What's interesting about this is, this is the spools SV process. And one of the things you'll see here in the next session is that we can actually see that they loaded the automation DLL. So when the Empire agent injected itself into the spools SV process, it brought with us the automation DLL. So if you do any sort of DLL load monitoring and alerting, one of the good techniques in this case could be maybe looking at the loads of automation without, PowerShell being the process that's doing the loading. Certainly if spools SV starts loading the automation DLL, you should probably call somebody. So here's just a quick example of the level of granularity that you can get with ETW. I'm not going to spend a ton of time here, but on a per thread basis, you can see, within the spools V process, which thread was actually responsible for doing the domain lookups, as well as doing any sort of file system activity. Everything here can be traced back not only to the process, but the individual thread. So for things like process injection, you actually have a pretty decent means of looking at that and then narrowing it down to the individual thread. So here's, all the commands. So even though we're not in a PowerShell process, but because we're running PowerShell commands, we're still getting that. So in this case, we ran invoke Mimikatz, so we can see this right here on the screen. But what's nice is just because we're running the automation DLL, we're also getting event logging. So here I'm just looking at script blocks. And in this case, what we see is, we now get the full Mimikatz script block logging here set in our session. So again, this is PowerShell commands being run out of the spools SV process, but still being logged with ETW. And so one of the last things I built into this, because as I walked through this demo, I realized how hard it is to actually follow some of this, because a lot of it has to do with injection and processes launching other processes, is it would be really interesting to be able to graph out, what this actually looks like. So in this case, we see, unknown 1924, which is the spools SV process. These are all the child processes of it. Similarly, if we start back from the beginning, from our first PowerShell instance, we build a graph off of that, we can really see our attack visually. So we start with PowerShell, then we ran conhost whoami CERT which is what downloaded and executed GPP password, and then we ran run as to elevate our privileges. Then we spawned a command shell that was then used to open Notepad, write the launcher.vbs, and then run it with cscript. Cscript then invokes PowerShell, and then ultimately spawns conhost, because that's how we're interacting with our first instance. So this is just a nice visual way of seeing what the data we captured with ETW. So behind each one of these, though, is a process object that maps back, what file system activity, what domain lookups, what threads were created, all different things that were available to us. So that was our demo. I'm just going to jump back here. So we have one more slide on ETW, or I guess two more slides on ETW. So this one is around .NET visibility. So we talked about Sharpsploit earlier and how it kind of bypasses a lot of the PowerShell logging and PowerShell blue team capabilities that are built into modern versions. One of the nice things I found, though, is that there's a .NET ETW provider. So there's a couple of them. This one I used .NET Runtime. And I started a session and I ran this specific command where Mimikatz invoke all. Because the source code is available, I actually went and looked at it. What's important is you see here it starts with logon passwords and a call to the function, and then it runs samdump, LSA secrets, LSA cache, wdigest. Before I show you the results, one thing to notice is this is another provider that generates a lot of data. Without filtering in place, it will actually look at every .NET call stack and log it to ETW. So it's a ton of information. But if you parse it out, you can actually see all the different .NET methods and calls logged in ETW. So we see, first one was here, we ran all. It starts with logon passwords. This is the function call, and then calls this command if we were to look through the source code. At that point, Mimikatz has not been loaded yet. So these methods are all the loading and calling of Mimikatz initially by Sharpsploit. And then finally, we get back after we do get export function. That means we're starting to execute Mimikatz. You'll see in subsequent order, samdump, LSA secrets, LSA cache, wdigest. So in this case, we're logging in sequential order what matches the source code of what we're actually running under the hood. So .NET actually provides a really good provider if you're looking to map back activity.
All right, so to wrap up with quick takeaways, first, as we had started out, PowerShell has really come a tremendously long way, and it's kudos to everybody who's in the research community driven that forward. It has better auditability than any other language. That doesn't mean attackers are going to stop abusing it. Auditability is not the same as prevention, but it does, I think, drive attackers that are really keen on being covert to look at other options like .NET. The second is something that we found in recent years through working with a lot of organizations, which is that really starting with a baseline of understanding all the sources of legitimate PowerShell activity in an environment is critical before doing detection. And as more and more tooling legitimately uses PowerShell, and as more system administrators learn and use PowerShell for their own one-off scripts, if you don't understand what's the normal hum of activity in an environment, it's really hard to determine what's malicious and what's standing out. And then finally, as Matt just walked through, ETW is a great place to immediately look the moment you're exploring a new technique. There's almost always a provider for a new source of operating system activity that you can look to start understanding what Windows is capable of capturing, and then walk your way back from that to a technique that can actually be applied for more regular monitoring and auditing. All right. We wanted to both thank everybody for joining us today, and especially to BruCON for inviting us back. It's always a highlight of our years to be able to come out here, so thank you all.
Okay, thank you, Matt. Thank you, Ryan, for the awesome talk. And I'm looking forward to see some interesting exploits or like red team assessments with DSC core. Maybe next presentation. We still have got time for a few questions.
Sure.
Do we have questions from the audience? 1 second.
Hi, thanks. So is this something where you could do this technique for the detections effectively at scale, or is it purely one-off focused stuff?
Are you referring to ETW?
Yeah.
So if you're like trying to write your own endpoint agent, you can absolutely subscribe to ETW and opt into the specific types of events that you want to collect and monitor. Or you could trigger a collection using tooling like what Matt created.
So there's a couple different ways to do it. If and there's a lot of filtering that you can apply to ETW that makes it a lot more manageable, especially when you're only looking at it from a forensic perspective. Remember, ETW was built for application performance monitoring and troubleshooting, so narrowing down and kind of removing all of the forensically irrelevant stuff gets you down just to what you need. And then you just have two options of how you want to view it. So you have the real-time parsing, which is a bit more complex, but allows you to do things like detection of events as they take place, or you can just log those events to a file and then use it, if you need to do a post-compromise assessment to figure out what's going on.
So at this stage, it sounds like it's effectively you've got to roll your own, and there's nothing doing that out there at the minute.
There are tools that do it. They just don't always advertise that they're using ETW under the hood. So like a lot of the sysinternals tools that you may be using today, when they just normalize those events, they're turning on ETW in the background. It's just not always made.
The nice thing is you don't need to load a driver to get that sort of introspection and visibility. You don't need to hook events that you'd otherwise normally need to hook.
Thank you.
Yeah, thank you.
Yeah, okay, thank you. If there are any additional questions, you can probably answer them off stage.
Yeah, we'll be grabbing a beer in the lobby, I'm sure. So.
And our next talk up is,
Thank you.
yeah, thank you.
This is you.